Hello, Mr. Ryan, are you right?
Yeah.
Okay, so we given this maze which only contains 0 or 1's. And originally,
Zeros and ones.
okay, 0's and 1. Okay, originally you are at top left corner. Okay, so you're here. Eric and Ryan, yeah, you are here. And for each move, you can move right, one position to the right, or move one position to the down. So you can only move to the east or south, okay? One position. And the destination, obviously, yeah, right? You can't cross borders. This is your destination. So I'm just asking, can you find the path? Can you find the route that
Right down, right.
and then listen, can you find the route? Is there such a path that you when you cross the path, when you walk through the route, you meet equal numbers of 1's and 0's? Okay, so equal numbers of 1's and 0's. Equal 1's
Yeah.
and equal
The one
0's.
that just Ryan just said.
What's that?
Right down, right.
Yeah.
Right down,
Right.
right.
Down, right.
Okay, so how many 1's?
3.
How many 0's?
3.
Okay, another one. Right, down, down, right. Okay? Okay, so this is a small maze. Yeah, obviously we can look at it, but if it's a very big one, so what's your thought? One hint is that you can only move 2 directions. It's not like 4 directions. It's just 2 directions. You can only walk to the right or walk to the south. We have been talking about a similar problem before, right? We are trying to find out how many ways we can choose from the top left to the right bottom.
Yeah.
And also we mentioned if we want to bypass, if this route needs to bypass one certain point, right? We talked about it a long time ago, we used the combination. So for example, here, there are 3 rows, here, there are 4 columns, right? To sum up, you need to make 3 downs and 4 rights in order to get to this point, right? So this is kind of like combination problem, am I right? Let's to calculate the number of ways from the top left to the right bottom. But this problem is slightly different. We want to find out if there's a such path that when we can walk on it, we have these equal numbers of 0's and 1's.
Yeah.
So any idea? Just random source. Any idea?
Brute force.
Yeah, brute force. We can brute force. But tell me, how do you brute force?
Check every possibility.
How do we check every possibility? So if I'm at here, how many possibilities do we have? At each point, how many possibilities? At each single cell, how many possibilities?
2.
Yeah, 2. So for each one, we have 2, right? So let's say we have a function, depth first search, right? Depth first search and breadth first search. Remember what's depth first search? What's breadth first search?
Depth of search is going at deep as you can, and breadth of search is going level by level.
Okay, so by thinking about that, which method is suited?
Breadth of search.
We are what? Depth first search. Because depth first search, look, we are trying to find out if such paths exist. Depth first search, we just walk down a route until we find one, right? So depth first search. Okay, let's coordinate R, C, and B. Can you guess what are these values?
Rows, columns, and
What's this? Okay, so think, what's this? Yeah, rows, columns. This means that.
Both.
Look, okay, so I'm saying this function returns that.
between.
Both.
Banana.
Okay, come on.
Big
Okay,
belly.
very close. Okay.
Biscuits.
Depth first search. I'm saying this function. I'm defining a function that can tell me if there's a
Bin.
path.
Bin.
Wait, this function returns true or false, right? It tells me.
Box.
It tells me.
Binoculars.
Come on, listen. It tells me if I can find a path from RC from this location to the right bottom, right? RC, yeah, that's a good guess. It's rows, column. Which partition, right? B. How about if I say it's balanced? Can you tell me what does it mean? Balance.
It means they're balanced, really. It
Balance.
means it's equal.
Balance. How about if I say, okay, if I can.
Yeah, balance means equal, kind of like it's like the same value.
Balance. What's balance?
It's kind of like like it's equal and
Yeah, it's equal. Yes, you're saying.
yeah, that's what
Okay.
I said. And also it has the same value.
Okay, so in order to find a path, so this balance needs to be.
Or you can balance on
Okay, come on,
the
listen.
beam
Yeah. Listen.
or be on the beam, and then you can balance so you won't fall off.
Okay,
and
so.
also both.
Yeah, balance. Okay, so what's this? This is balance. Okay, so in order to find a path, this balance needs to be
Equal.
equal. And what's the usual value we represent the balance is equal? What should I put here? Well, what are we looking for? Come on, it's a balance.
1's and 0's.
So, okay, so this is 1's. How many 1's? How many 0's? Okay, how many 0's? How many 1's? Okay, so in order to find the path, we need this balance to be 0, right? Balance value. Here, this is 0, right? So how about 0? Then I said minus 1. Because it's 0, okay? Minus 1. We said this is positive, yeah? Positive. This is negative. If we meet 1, 0, we decrement the balance by 1. If we meet 1, 1, we increment the balance by 1. And the number of equal 0's and 1's, it means that the balance will be 0, right? Look, plus 1, plus 1, plus 1, 1, 1, 1, there are 3. 0, 0, 0, minus 3. 3 plus minus 3, 0. Make sense? So here,
You don't use that 0, you use the 0 at the bottom right corner.
good point, yeah, but I'm trying to say, look, yeah, that's a very good point, yeah. Look, I'm trying to say at this point, we are here, DFS 0, 0, and the balance will be minus 1, right? The balance will be 0. The balance will be 1. The balance will be 0. The balance will be 1. The balance will be 0. When we reach this point, we check if this balance is 0, right? If it's 0, it means that we have equal number of 1's and 0. Make sense? Yeah. So to sum up, when we meet 0's, we decrement the balance by 1. When we meet 1, we increment the balance by 1. Okay? Okay, so then this is the depth of search. Okay, and we can solve this using buffer search, which I'm going to talk about in the next lesson. Okay, on depth of search.
When the next year.
Yeah, which is tomorrow.
Next year.
Yeah, tomorrow and next week. Okay, so let's look at this, and then you can improve it later. Okay, this is quite similar to some problems we have talked about before, right? Depth of search, RC balance. Balance plus equal 1 if this maze RC is 1, right? Is 1. Else we need to minus 1, right? Okay, so this means that if the maze current position is 1, we increment the balance by 1. Otherwise we decrement, right? So we can also do this. B plus equal, because it has only two values, minus 1, 1, and then maze, we can do this RC. Because this is a tuple. Tuple contains two values. Tuple 0 is minus 1. Tuple 1 is 1, right? So, and we use this tuple, and we use the value of the maze to retrieve the value of the minus 1 or 1. And then if B plus equal, and then we need to check if R equal rows minus 1. If it's the last row, and if the columns C equal columns minus 1. If it's the destination, then we need to return if B equal 0, right? Okay? Now, look, I'm at this point, right? Depth of search, RCB, right? I'm moving down, so what's this? Depth of search, R plus 1, C, B, right? I'm moving right, this is what? Depth of search, RC plus 1, B, am I right? There are only two positions, right? Yeah, but we have to check the boundary. If R smaller than rows and depth of search R plus 1 CB, then we return true. And similarly, if C plus 1 R plus 1, okay, R plus 1 is smaller. If C plus 1 is smaller than columns and depth of search RC plus 1 B, then return true. Okay? Otherwise we return false, right? Look, does it make sense here? Look, we are at this point, recursion, right? I'm at this point position. I'm here. So I have two choices. I can go down or I can go right. I can go down or I can go right. Right? Go right. So if I can go down, I call this depth of search. If I can go down, I find the path, then I immediately return true. I don't need to try the other route, right? Make sense? Because the question was asking, is there such a path? Do I need to brute force all the paths? No. If I find a path, then I just know it. I don't need to try other paths. This is the depth of search. If I can walk down, and if by walking down, I have a path. I know there's a path. Then I return true. Okay. If there's no path, I need to try walking right. Right. I need to try walking right. Okay. So this balance thing is updated here, right? At the beginning of recursion, right? Instead of updating here. Okay. So is there a problem with this approach?
Yes.
What's that?
Does it just keep on going right?
Sorry.
Does it just keep on going right or just keep going down?
There are two, yeah. Each position I can have two paths. But is there a
Cache?
yes? Why? Yes, exactly. We need to put a cache here to make it dynamic programming. Otherwise, this is a this is a brute force. Putting a cache. This is the top-down dynamic programming. Why there is a duplication? We need to remember. Okay.
It's a bit messy.
That's okay. Okay, let's look at this point. So how many ways from here to here? There are a lot, right? So here, 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 here. Suppose here, I know there's a path, right? There's a path. I already calculate this. When the balance is 1, I can't find the path. But the thing is that there are many times that this point is passed. We need to cross this point. Therefore search RC balance. So the first time we cross this point, for example, this value RC balance, we know there is no path. There is no such path. The second time we cross it with the same RC balance. Do we need to do this again? Suppose this is huge. This is a very huge area. It takes like an hour to calculate RCB. Okay? So we don't, right? We don't, because we already know there's no path. Okay? If there's a path, we return immediately. We don't need to cache actually. But if it's a false, if there's no path, we don't want to spend time calculating it again. Because we already know, we tried last time, there's no path. We remember, there's no point to keep trying. I might say here, this point, there are lots of ways. Eventually we'll come to this point, right? Yeah? Okay? The first time we calculate the result, we remember it. So look, the time complexity, without the cache, this is exponential, right? Ryan, exponential, because each point would be computed many times. It's exponential. But with this cache, the number of total states we calculated is rows times columns, right? Because each position, when we calculate it, we store it. How many numbers in this maze? R times C, right? But we need to remember the third one is the balance. Time complexity is RC times balance, okay? This is the range. Okay? The space complexity, obviously, the same. Yeah? We need an array to store it. This is top-down. We're using a cache. The computer does the job for us. The computer maintains the notebook for us. But we can do this in bottom-up dynamic programming as well. The opposite, bottom-up. Bottom-up is non-trivial to write, to implement. Top-down is easier. Top-down is easier because we just put in a cache. This is the magic keyword to turn this brute force into top-down dynamic programming by remembering. This is quite similar and Fibonacci number, right? Remember Fibonacci number. Fn equals Fn minus 1 plus Fn minus 2. Yeah, look, quite similar. Look, in order to calculate Fn, we need to two recursive call with a smaller problem, right? With a smaller problem. Yeah, this is quite similar. Look, at each location, we need to solve two recursive functions. If it's responding to 2, we need to remember. But if it's responding to 1, we may not need to remember. Another example why we may not need to remember. The factorial. Fn equals n times Fn minus 1, right? Do we need to put a cache here?
No.
Probably no, right? Probably no, because each Fn is only calculated once. If you want to calculate F4, you need to calculate F3. In order to calculate F3, you need F2. In order to calculate F2, you need to calculate F1, which we know is 1, right? So when we get a 1, we come back to calculate F2, come back to calculate F3, F4. But when we calculate F4, F3, F2, F1, it's only calculated once, am I right? But here, why is it calculated more than once? F4 equals F3 plus F2. F3 equals F2 plus F1. You see the problem? F2 here, F2 here. Okay? So we need to calculate. Otherwise, we spend time recalculating it. F2 equals F1 plus F0. Okay? Look, F1 again. Okay, so what have you learned today?
I learned about a maze.
Problem. So what are we trying to do? What kind of solution we have? And that's it.
There's mostly there's 1's and 0's, and there's numbers like 1's, 0, 1's or 0's, or 1's and 0's, and so we're gonna reach the top left is the start, and top and bottom right is the destination. And so we want to have our path must have. We want to know if is there any possible path that the path contains the same number of 0's and 1's. We can do brute force, and we can do top down.
Dynamic programming.
Yeah.
Dynamic programming. What's dynamic programming?
Remembering.
Yeah, the key thing is remembering and reusing the intermediate results. Okay, this is dynamic programming. Solving the smaller size problem. Okay, another thing is there. Look, we're working from the top left to the bottom right, and we can also do the opposite. Working from the bottom right to the top left. It's the same, right? We talk about finding the nearest exit in the maze. We can start from the entry to find the exit, or we can start from any exit to find the entry. This is bi-directional, right?
Yeah.
Okay, that's it for today. Happy New Year! Happy New Year!
Bye.
Bye.